I'm going to switch gears now and I'm going to talk about the problem of testing compilers, in particular testing compilers for GPUs, although basically everything, almost everything I'm going to tell you is more generally applicable to testing compilers. So first of all, I hope I don't need to convince you that reliable compilers are important. Everyone depends upon compilers. Even my mother depends upon compilers, even though she doesn't know it, right? Every bit of software we're ever using has pretty much been compiled. And if you're a formal verification person like me, you often implicitly assume compiler reliability. To give you two examples of that in my previous talk on GPU Verify, we're verifying this source code and we're then not taking account of the actual GPU platform it's going to run on. So we might verify some data race freedom properties of a piece of source code that's then going to be miscompiled by a compiler from a vendor and is going to actually have data races when the code runs on a GPU. That's one possibility. It also is the case that we're relying upon the Clang front end in our verification tool. And if the Clang front end had a bug that meant that the LLVM IR we work on is actually not in correspondence with the source code, then our verification result would be limited. So reliable compilers really matter. And what I'm going to do first of all is talk to you about two successful compiler testing methods that have been particularly successful in recent years: random differential testing and equivalence modulo inputs testing. Equivalence modulo inputs testing is an example of something called metamorphic testing, and I'm going to tell you about my recent work on applying metamorphic testing to graphics compilers, recent work with my PhD student Andrei Lascu and some other members of my research group. Okay, so random differential testing is a very simple idea. The idea is you generate random programs using some kind of fuzzing tool that knows how to generate programs. So let's say we generate random C programs. You then try those programs with multiple compilers. So for example, you might use GCC and LLVM to open source compilers, the Clang front end for LLVM. And you might use a couple of commercial compilers like Microsoft's C compiler and Intel's C compiler. And you could compile this single program with all of those compilers and run the resulting executables. And let's say that the program has been designed to print a number. If we find that all of the compilers end up producing a program that when executed prints the number 24, except that Clang prints the number 42, then we know that Clang is the correct one because obviously 42 is the right answer and the other compilers are obviously wrong. Right. So actually, what do we know if we see this? What are the possible things we know from this information? Okay, so first of all, the program random.c might exhibit non-determinism. Let's say it doesn't, then what do we know? Okay, so more generally, there might be implementation-defined features in random.c that the compilers disagree on, which might legitimately mean they have different results. Pseudo-random generation could be something. Integer width could be another one. Right? Let's imagine that they all agree. Then what do we know? At least one compiler is wrong. Okay? So if the program is well-defined and deterministic, all the compilers agree on implementation-defined matters, and they disagree on the results, then at least one of them is wrong. And it's probably Clang. But of course, they might all be wrong, or it might be that Clang is the only one that's right. But we know that something is wrong in this case. So the idea is that result mismatches indicate compiler bugs. And this is an old idea, but it was really made practical by this tool called CSmith from the University of Utah that is a generator of random C programs that are guaranteed to be free from undefined behavior, making them suitable for testing compilers. So as we already discussed, compiler testing is complicated by this undefined behavior problem. If the random program exhibits undefined behaviors, then it's not necessarily indicative of a compiler error that we get different results when we run the compiled binaries. So because if a program's got undefined behavior, then any result is acceptable. And I want to take a little detour into undefined behavior because I think this is a really interesting and underappreciated topic. So what I'm going to do is go into Visual Studio, which I'm just going to be using as an editor here. And what I want to do is implement a saturating addition function, a function that takes two integers, x and y, and adds them together. But if the result would be too large to store an assigned integer, I wanted to give the maximum possible integer. If the result would be too small, I wanted to give the minimum possible integer. And otherwise, I wanted to return x plus y. Okay? So, anyone suggest how we could go about doing this? Just using regular C operators. Okay, so what we might do is something like the following. We might say, if x is greater than 0, and y is greater than 0, and x plus y is less than 0, right, then the result must have been too large because we got an overflow. So return int max. Okay? So we've got two positive integers. We add them together and find we get a negative result. Therefore, the result must have overflowed. So we can instead return int max. And if we find that x is less than 0, and y is less than 0, and x plus y is greater than 0, then return in min, otherwise return x plus y. Okay? So this seems like maybe a reasonable way to implement saturating addition in C. Okay, of course, I wouldn't be showing you it if it was, but it looks like it might be. So if I go into Cygwin here, I'm going to compile this with GCC. Okay, so if I run it, says the saturating add of 1 and 2 is 3. Okay, good. Let's try something a bit larger. Okay, the saturating add of these two numbers is some bigger number. Let me make them a bit bigger still. Okay, I'm going to keep making them bigger and bigger. And here we go. So the saturating add of this big number and itself is this number here, which you might recognize as the largest number you can represent in a 32-bit signed integer. Okay, so this seems to have potentially worked. So now let's compile the program again, but with optimizations enabled, maximum optimizations. So now I see here that the saturating add of these two big numbers is actually this negative number, right? So without optimizations, we got the effect we wanted. We got the saturating addition for exactly the reason I said, which is that we did the addition and it overflowed. So we detected that two positives are given a negative, so we returned integer max. But this hasn't worked with optimizations enabled, right? Now, this might look like a compiler bug, and you might go and file this as a GCC compiler bug. And if you did, you would get very unfriendly response from the GCC compiler developer, because I think they're very fed up of getting people reporting bugs, which are not actually bugs. They're actually instances where the program has got undefined behavior. So in C, having a signed operation overflow is an undefined behavior. If your program would exhibit a signed overflow, then not only is the result of that overflow undefined, but the result of the whole program execution is undefined. And you read people writing some very unhelpful remarks like, in the presence of undefined behavior, the compiler can do anything it likes, it can launch a nuclear missile, it can format your hard drive, etc. And I think those remarks are really unhelpful because they give the impression that the compiler is somehow against you, that it's trying to go, ah ha ha ha, I can see undefined behavior, I'm going to do some strange thing to your program. Actually, that's not what the compiler is doing at all, but the compiler is clearly doing something that may seem counterintuitive. So let me try and shed a little bit of light on that for you. So now I want to show you what we might call the compiler's thought process. Of course, this isn't really a thought process, it's just a bunch of compiler passes interacting. So the deal is, if the program has got undefined behavior, it doesn't matter what it does. It doesn't matter what the program does if it's got undefined behavior. So the compiler isn't looking for undefined behavior and saying, aha, I'm going to do weird things. It's rather going to say, I'm simply going to assume there is no undefined behavior. Because if there is undefined behavior, it doesn't matter what the program does, so I can just assume there isn't any. And I can optimize the program as best I can under that assumption. If I do good optimizations that make well-defined code go faster, that it doesn't matter if those optimizations make undefined code behave differently, because it doesn't matter what the undefined code does. So let's go through this example with that in mind. So we have this implementation of saturating addition. And the compiler says, okay, I will assume this program does not exhibit undefined behavior, because if it does, then it doesn't matter what code I emit. So I know that x plus y doesn't overflow, because I know that if x is positive and y is positive, then the only way x plus y could be negative would be if there was overflow, which is undefined. So I know, therefore, that x plus y does not overflow, given the assumptions I'm making. So the condition of this if is equivalent to false. Okay, that's really good, right? Because if I can say something is equivalent to false, that means I can potentially aggressively optimize it. And by similar reasoning, the second condition is equivalent to false, right? The fact that if you've got two negatives and you add them and get a positive, then there must have been an overflow. And there isn't going to be overflow because there isn't going to be undefined behavior. Or there might be, but I don't care. Okay, so I can simplify the program to if false, return in max, if false, return in min. Or even better, I can simplify it to just return x plus y, right? And actually, the compiler gets a special sticker for doing really well at its job. The compiler's job is to optimize your program under the rules of the language, and the language says it doesn't matter what you do if there's undefined behavior. So the compiler's actually unwittingly undone precisely what we tried to do to implement saturating addition, and it's given us non-saturating addition. And of course, on an x86 processor, the add does give a negative result when the result overflows, so we end up getting the negative result I showed you. Does that make sense? Okay, so I hope this has shown you something about what compilers do with undefined behavior and why, if we want to test compilers, we've got to be careful to make sure we test them on well-defined programs. With intended overflow, you can do it with unsigned, but not with signed. So unsigned overflow is well-defined, and it gives you modular arithmetic. But with signed, it's undefined, and yes, you can't rely on it. Well, you can rely on it if you know which compiler you're going to use, and you know you're not going to upgrade your compiler version. So, and people do, but it's dangerous. Okay. So, also, undefined behaviors have an impact on program analyzers. So, as I mentioned before, we saved an enormous amount of time using the Clang frontend for GPU verify. There's also a tool called SMAC that translates LLVM bytecode into Boogie to allow modular verification of C programs. And SMAC, again, benefits from the LLVM Clang frontend. Okay, however, the problem is that the compiler frontend, even though it's not the full-blown compiler, it already starts to assume you don't have undefined behavior in your code. So for example, if you write this little dodgy GPU kernel, if 2 divided by 0 is equal to 2, then write my global ID to A0. Okay? So if you imagine lots of threads writing their global ID to array A at element 0, that kernel would clearly be full of data races. Everyone is trying to write to 0. Now, is this code reachable? Well, the answer is it depends on what 2 divided by 0 means. 2 divided by 0 could throw an exception, in which case it's not reachable, but it would be reasonable to assume that that condition could evaluate arbitrarily, in which case the code would be reachable and there would be a data race, right? So from a point of view of program verification, we want to say, in the case of undefined behavior, we should assume the worst and imagine that anything could happen. But the Clang frontend is going to actually say, I'm going to simply remove that whole bit of code because it doesn't matter what I do, right? So GPU verify, if you run it on this program, the Clang frontend does, to do it correctly, give a warning saying division by 0, but only a warning. And then GPU verify gets given an empty kernel to verify. And GPU verify quite rightly says that's free from data races. Okay? So I'm not going to show you this running, but basically we're depending upon Clang, and Clang is assuming undefined behavior means it should remove code in this case, which is fine from a compilation perspective, but from a verification perspective, it's not so good. So you need to be careful about undefined behaviors when we're using compilers, compiler infrastructure in our program analysis tools. Okay, so relying on compiler frontends can render a would-be sound tool unsound. And we just need to be aware of that when we make claims about soundness of our techniques. I claim GPU verify is theoretically sound in the sense that under appropriate assumptions and a perfect implementation, it's sound. I don't claim that the practical tool is sound because it depends on a load of infrastructure, and of course there'll be bugs in our bits of the tool as well. Okay, so the next technique I want to tell you about is a really clever technique that was published at PLDI 2014 by Wu Li et al. And this is called equivalence modular inputs testing. So the idea here is, let's say we've got a program P, and let's assume that P is well-defined and it's deterministic. And what we do is we then compile P, and we also run the compiled code through a profiler with respect to a given input I. And because P is well-defined and deterministic, this profiling process gives us a partitioning of the statements of P into 2 disjoint subsets. The statements that get covered by the input I, and the statements that don't get covered by the input I. So what I mean by covered is that when we execute the program on that input, at some point we execute each of the statements in the top part of the partitioning. And we never execute the statements in the bottom part of the partitioning. So do you agree with me that if P is well-defined and deterministic, every time we run P on I, we'll get the same partitioning? We're not going to get some statements covered on one run but not on another run if we fix the input. Yeah? Well, we've compiled the code, so we don't recompile the code. So having compiled the code, we then run again and again. Yeah? So we're going to get this same partitioning. So let's call the statements not covered by I, let's call them D for dead. They're not necessarily dead code in general. They might be reachable for other inputs, but they're dead with respect to that input I. So the observation that these researchers had is that from the program P, we can make a load of programs, P1, P2, P3, as many as we like, that differ in D. We can take a statement inside D, and we can, for example, remove it, or we could mutate it by applying a mutation operator like we saw this morning, or we could replace it with some new code, as long as the variants are syntactically correct. What was the term we were introduced to for that? I think we had to say that they're not stillborn mutants, right? If I remember rightly from what I learned this morning, okay? So as long as these are not stillborns, then they should behave identically to P on input I. On other inputs, they might behave completely differently, but because we only messed with the D part, the part that was I dead, these variants should behave just the same as P did when we run it on input I. Agreed? Okay, so if we compile just with one compiler this time, we don't need multiple compilers. If we compile all these variants and execute all of the variants on I, then if we see a mismatch, we know that there is a compiler bug, and it's almost certainly the case that this program is the one that's inducing the compiler bug. I mean, of course, it's theoretically possible that somehow that's the only program the compiler compiled correctly, but that seems even less plausible than the case where Clang was the only correct compiler in the last example I showed you. Does the idea make sense? Could this idea have been done in the 1980s? But did anyone think of it? So I love this paper because it's such a simple idea. And when I read the paper, I just thought, I wish I had that idea. It's such a cool idea. Okay, well, you might ask, does it work? It does work. It finds lots and lots of compiler bugs. The basic reason is that it makes the control flow graph of the programs different and complicated, and that can expose bugs in optimizers. So I think this is a very cool idea. It's one of those ideas where I think anyone could have thought of that idea, but they didn't. Okay, so this is an example of something called metamorphic testing, which I'll come to in a second. So what we did at last year's PLDI is we took these random differential testing and metamorphic and equivalence modular inputs testing ideas, and we wanted to apply them to testing OpenCL compilers for the GPU programming language OpenCL. And we discovered a whole load of compiler bugs in compilers from all of the major vendors, OpenCL compilers from all of the major vendors, and we reported these bugs and in general got a positive response. Many of the bugs have now been fixed, which is good, but it makes it harder to demo compiler bugs because you get new drivers and now you don't have the juicy bugs you used to be able to demo. Okay, and this is an aside, but actually these compilers are components of the device driver for the GPUs. So because the device driver's got a little compiler inside it that knows how to compile OpenCL at runtime. As part of that work, we wanted to lift this EMI idea, this equivalence modular inputs idea, to OpenCL. And we realized this was going to be hard because for EMI to work, you need to have input-dependent code. And not only do you need to have it, but you need to be able to detect that you've got it. So to make this work for OpenCL, we would have needed, first of all, a profiler for OpenCL that could do code coverage and tell us what code was covered and what code wasn't covered. In the last lecture, someone asked the question about whether you can do debugging of OpenCL kernels running on a GPU. The answer was, not usually. So code coverage is also hard. Sure, we could implement our own code coverage tool using a simulator, but we didn't want to do that engineering work unless we had to. The other thing is that based on our experience of GPU kernels from the GPU Verify project, we know that it's just not that common to have bits of code that are unreachable for some inputs in a GPU kernel. It's perfectly legal, and it does happen from time to time, but it's generally not good practice in terms of getting high performance because branching can be quite expensive on GPUs. So we realized that it was going to be hard to apply this technique. So we had a different idea, which was rather than find dead code, why don't we go make our own dead code up? Just manufacture dead code. And this idea, I think, is actually quite a simple but effective idea that has led to quite a lot of follow-on research and is applicable not just to GPU programming languages, but to compiler testing in general. So here I'm showing you a little piece of OpenCL code that I've grayed out because I don't want you to read it. I just want you to look and observe that it's code that someone wrote. It's not some random piece of code that was generated. It's an actual existing piece of code. And what we do, and what we did in this PLDI work, was we extended a function, like this breadth first search kernel, we extended it with a new argument, a global array of integers with the name dead, which might hint at what we're going to use this for. So this is an array of integers, and the compiler that compiles this piece of kernel code has got no idea what's going to be in that array. It just knows it's an array of integers in global memory. And then what we do is at randomly chosen points of the program, we add a condition that says something like, if dead at index 43 is less than dead at index 21, then execute some code. Okay. So if it were possible for that condition to be true, then we would fundamentally change what the kernel would compute, depending on what we put inside that conditional. If we make sure that this condition can't be true, then this should not change what the kernel computes. It might change how efficiently the kernel runs, it might change, and hopefully will change, the optimizations the compiler does, but ultimately it shouldn't change the behavior of the kernel. Agreed? Okay, so if in particular we fill dead up with monotonically increasing values, then we ensure by construction that at runtime that condition is going to be false. At compile time, the compiler doesn't know that we're going to do this runtime trick, so the compiler can't optimize away this code. And furthermore, if we inject code in here, in such a way that we make that code read from and write to data that's declared outside, then we actually give the compiler the opportunity to try and do optimizations that cross the boundary of this injected block of code. And it may trip up doing those optimizations, and this may allow us to expose bugs in the compiler by observing that this mutation causes differences in the behavior of the kernel. Okay, so we can inject randomly generated code in here, or we can inject code that's been transplanted from another kernel, as long as we make sure that whatever we inject is syntactically correct. So this is an example, again from what I learned this morning, of making an equivalent mutant. So we're doing some kind of mutation of the program, but we are setting out to make an equivalent mutant because we want to know that we should not observe a difference. If we do observe a difference, that indicates there's a bug in the compiler. Okay, assuming that this program was already well-defined and deterministic. What you've got to be really careful of is that whatever you inject has got to be free from undefined behaviors. So indeed, you can inject well-defined code that will do computation as long as it will not propagate its values into the actual final result of the kernel. And then if you don't then write that result into an output array, or then indeed that would be another example of a semantics preserving transformation. My point is only that you might think, well, why not use a fuzzer to generate random bits of code and inject them? If you did that, you'd have to make sure that those random bits of code weren't going to exhibit undefined behaviors. Because if they did, the compiler could, in principle, start to remove whole bits of, it could start to do its crazy optimizations, yeah. But no, that's a really good idea, and that's something in what I'm going to show you in a minute that is sort of like on my to-do list to implement next, live code injection. So there are various things we could do. This was just the first thing we did. Okay, so now I want to give you a detour into this thing called metamorphic testing, which was originally proposed in the late 90s and has seen a bit of a surge in activity recently. There was a first metamorphic testing workshop a few weeks ago at the ICSI conference where we had a little paper. And okay, suppose we want to implement the sign function efficiently for floating point numbers. So imagine we don't have a reference implementation of sign to check our implementation against. If our implementation says that for a given x, the sign of x is y, then how do we know whether our implementation has computed sign of x correctly? We might know what the sign of x is for certain values of x, but for some arbitrary value of x, we don't know what sign of x should be. Therefore, we can't check whether our implementation of the sign function has given the right result or not. Okay? This is called the oracle problem, the test oracle problem. So we don't have a test oracle, so we can't know whether a particular implementation is correct or not. So this has got nothing to do with compilers, by the way. This is a detour. Okay. But what we do know, for example, is that for the sign function, the sign of x is the same as the sign of x plus 2 pi. We know that's a mathematical property of the sign function. So what we could do is test our implementation with some value x and with x plus 2 pi. And if we find that we get different results, then we know our implementation of sign can't be correct. We obviously have to make sure we take account of floating point rounding error here. We would have to have some kind of fuzzy equality that uses an appropriate epsilon to say whether the result is acceptably close. But in principle, we can imagine that we can use inequality between these should be equal values to find bugs in our implementation of sign. This, of course, can't help us establish that our implementation is correct. If we could just say that sign of x is 0 for all x, then it would certainly pass this test. Okay? But if we actually do a decent job of implementing sign, but it's a bit flawed, we can use this identity of sign to identify bugs in our implementation. Does that make sense? Yep. So it's a pretty simple idea. And we could say that x maps to x plus 2 pi is a metamorphic relation of the sign function, or a metamorphic transformation for sign. And more generally, let's imagine we're trying to implement some mathematically defined function f. And we know that there's some function g on the input space of f with the property that f of x has got to be the same as f of g of x. If we know that this must be true, then we can test our implementation of f using g. So we can say for a bunch of x's, is our implementation of f applied to x the same as our implementation of f applied to g of x? And if it's not, then we find a bug in our implementation. It assumes that g really is a property of the function. So I mean, if we were wrong, and yeah, I mean, if I gave you an example for the sign function that is true. If I'd said x plus pi, then it would be wrong. Oh, you mean we've got to actually apply g? Yeah, you see there's a bit of a chicken and egg problem here where we need to correct g to find bugs in f. Yeah, but the worst that can happen is that we waste time investigating. We find a mismatch, we go, okay, let's have a look, and eventually we conclude that we implemented g wrongly. Yeah, so you're right, but I don't think it's a big issue in practice because, well, a mismatch either indicates that this is indeed not a metamorphic relation or that it's a bug. Okay, So let's view compiling and running a program as a really nice function called compile and run. So compile and run is a two-input function. It takes a program and an input. And what it does is it compiles the program, returning the error message if the compilation fails. Otherwise, it runs the program and returns the program's output as a string. So it's a function from program and input to string. Okay, so what we can do, if we fix the input I, then we can, I think this is called currying, if my functional programming knowledge is correct. We can curry compile and run to get a function called compile and run on I, okay, which is a one-input function. It takes a program P, and it compiles the program and runs the program on the fixed input I. All right? So if F is a program transformation that preserves the semantics of P when run on the input I, then we've got the property that compile and run on I applied to P should be the same as compile and run on I applied to F of P. Okay? And here, F is a metamorphic relation on programs with respect to the function compile and run on I. So this is how we can view this program transformation-based approach to compiler testing as an instance of metamorphic testing. Make sense? Okay. So moving on. We don't have to do just dead code injection. We already heard from a gentleman at the back about the possibility of injecting live code if we're careful. Here's a really simple thing we could do. Seems too simple to be useful. Replace an integer expression e with e plus 0. That would clearly be a metamorphic transformation on a program. Okay? And you might think, well, surely any high-quality compiler would just blast away the plus 0. But we've got this dead array, okay? And we know at runtime what the dead array is going to contain. So this allows us to manufacture expressions that are guaranteed to evaluate to 0 or to 1 or to anything we like. Right? We can use this array that's opaque to the compiler to play tricks. So for example, we can make a 0 by saying, give me dead 0. Or we could get dead 1 plus dead 2 minus dead 3. Remember, dead I is equal to I at runtime, but not at compile time, in the sense the compiler doesn't know this. Okay, or we could do something more sophisticated if we wanted. So instead of replacing e with e plus 0, we could replace e with e plus a manufactured 0. For example, e plus dead 1 plus dead 2 minus dead 3. Does that make sense? So now, there's no way the compiler can optimize away this transformation. It's now a fundamentally different piece of code for the compiler, and this may change other optimizations the compiler is going to do. Okay, so there are lots of identity functions we could try. We could add 0, we could minus 0, we could multiply by 1, divide by 1. In OpenCL, there's a bitwise rotate intrinsic, and you could do something like rotate an expression e by x, and then backwards rotate it by x. Okay? And furthermore, you could apply identity functions to x and to negative x. So you could replace x with x plus a manufactured 0. You replace negative x with negative x divided by a manufactured 1. You can really have a lot of fun making really strange things that are guaranteed not to change what the program does, but you can give the compiler a really hard time by doing these strange things. Okay, and you've got to be a bit careful. So for example, the clamp intrinsic at OpenCL, you could say, I want you to clamp E into the range E, i.e. leave E alone, right? And you could then apply an identity function to each of the E's to make this quite difficult for the compiler. This is fine as long as E is side effect free. We're going to evaluate E 3 times instead of once. So E needs to be side effect free for this to work. So you have to be a bit careful, but you can have a lot of fun dreaming up these semantics preserving transformations. Okay, so this is a way of testing compilers. You take a program and you apply a load of semantics preserving transformations to the program, maybe using an opaque value like the dead array, or maybe not. There could be other things you could do, like you could just maybe make a very complicated Boolean expression that you've used an SMT solver to ensure is going to be false. And you could inject dead code using a complicated expression that the compiler, because compilers have got to be fast, is not going to determine is false, right? But you've used an SMT solver offline to determine is going to be false. Okay. So I argue that this is a very general idea. That think of your favorite language. Can you think of a way of injecting an equivalent of my dead array into your language, into programs in your language? I think the answer is probably yes. Right? In a C program, you could read from a file. In a Haskell program, you could inject a new argument. You know, there's always going to be a way of injecting stuff the compiler can't know about. So this should be applicable in basically any programming language. And now I'm going to kick off a little demo, which I'll intersperse with the rest of the remarks. Okay, so there are a couple more advantages of this technique, which I'll come to in a moment. So I've been interested in looking at compilers for the OpenGL shading language, and I'll explain in a moment why I'm interested in this particular language. But let me just start the demo first. So Okay, this is quite pretty, would you agree? Yeah. This is something from a website called glslsandbox.com. GLSL stands for the OpenGL shading language. OpenGL is this open graphics library, and it's a way of getting 3D graphics to be rendered using GPUs. And the GLSL, the shading language, is a little bit like writing kernels in OpenCL, except they're much simpler than OpenCL kernels. They've just got to make either pixels get transformed to certain, vertices of a scene get transformed to certain positions, or make pixels be rendered particular colors. And this is something that's actually just, it's very simple. It's two triangles making up a rectangle, and then the cool animation is entirely captured by pixel values, computed according to the current time and the position of the pixels. So some hobbyist made this. But you can imagine that this could be something that's in some important computer game, or could be something that's on the display of your modern car. Okay? So you might be a little bit annoyed if you paid good money for that car or game, and you've got something that takes a while to compile, because I've injected loads of stuff into it. That's why it takes a while to compile. Okay? But it would be a bit annoying if instead you got something like this. Or maybe you'd be pleased, because that looks quite nice, actually. That looks quite attractive. So maybe you'd be a bit annoyed if you got something like this one, which also takes a while to compile, and I think has a less satisfying result unless you're into modern art, in which case maybe you will prefer this. So these all should produce the same animation, but they produce different animations due to compiler bugs that have been identified by injecting things into these programs. So now I'm going to give you a little demo of the tool we built so far. So I'm going to show you another example. This is another cool thing from glslsandbox.com. So what I'm going to do is I'm going to run a little script called generate shader set. Okay, and what I give to that is three things. I give it a recipient shader. So I'm going to give it good.frag as the recipient shader. That was the fragment shader I just showed you, the circles. Then I'm going to give it a folder of donor shaders. So I've got a whole folder full of other shaders that are going to be used as donors for this dead code injection. And the tool is going to insert dead fragments of code, and it's going to put pieces of these other shaders into the shader. So what we do is we choose a little subtree of the abstract syntax tree of the donor. Okay? We run a visitor on that to say, what are the free variables in that subtree? Then if we can find an existing variable in scope that's got the right type, we randomly decide whether to either rename the variable in the subtree to be the name of that variable, or to instead just declare a fresh variable with the right type. Yep. So basically, we either substitute free variables with existing variables if available, or we declare fresh variables. And we use a bit of randomization to make sure we do a bit of both. Okay. And then the final thing is the OpenGL version number. So I'm using GLSL version 4.40 here. So, oh, and I'd say how many variants I want. So let's make 20 variants. And let's turn verbose on. So what you're going to see here is you might see a few errors in the mix here. It's generating a bunch of these shaders, produce 1 of 20, 2 of 20. Occasionally we get a problem due to bugs in our injector. So this thing of, as you can imagine, donating an AST fragment from one shader into another is quite a complicated process. So occasionally we've not gotten it right yet. And we run the Kronos Group's GLSL validator tool to check, at least with some confidence, whether the injected programs we produce are at least syntactically correct. Of course, if you're thinking hard about this, you might think, okay, well, what if we've got bugs in our injection? We might wrongly conclude the compiler's got a bug, right? If we've actually made non-semantics preserving transformations. And you'd be absolutely right, we do have to be careful of that. That ends up just causing wasted time. We investigate what we think is a compiler bug, and we eventually realize we've injected something that does change the semantics of the program, and we have to go back and fix our injector. Okay, so it generated 20 variants in 25 tries. And yeah, maybe when I fly to California tomorrow for PLDI, I'll fix those 5 tries. So let's see. Okay, and now what we can do is we can run this shader set. And what we've got to do is we've got to give a vertex shader, which I won't go to the details of here, and we give the shader set folder. And this is now going to produce, ideally, from Intel's point of view, but not ideally from my point of view, loads of those circles, and they should all be perfect. Okay? From my point of view, ideally, it's going to produce a few crashes, a few bad images. Okay? So what I want you to do is to bang the desk every time you see a bad-looking image. Okay, ready? Get your hands on the desk. Okay, go. Oops. Okay. I think there were two of them there. Right. Okay. So we'll come back to that in a moment. So So my first hypothesis was it's easy to apply this technique. You can always try it for your own language. You can always find a way of making it work. Next one is that test case reduction should be really easy. Right, so what I've shown you so far is that by doing something very questionable to some programs, we can make some bad images appear. Yeah, and you're right. If we've not done the injections right, then you would expect bad images to appear. Yeah. So hopefully I can convince you in the rest of the demo that we do find genuine compiler bugs. Yeah. And if our injections are semantics preserving, we should find genuine compiler bugs. Of course, if we implement the transformations wrongly, we'll get false alarms. Yeah. You can't turn off optimizations in an OpenGL compiler, as far as I know. So OpenCL you can, but OpenGL, it appears there's no way of doing it. Please, if someone knows otherwise, I'd love to know, because that would double the number of test targets we have, in a sense. You know, in a sense, you can regard a compiler with or without optimizations like two different compilers. But I would certainly expect, what I can tell you is that when we've done work on testing OpenCL compilers, we do indeed find bugs that only occur with optimizations enabled or disabled. Ironically, we actually found more bugs in OpenCL compilers when optimizations are disabled. I believe because people tend to always have them enabled, because you would never program a GPU in OpenCL. You would never use OpenCL unless you wanted maximum performance. So the optimization path is more thoroughly tested, I guess. Okay, so test case reduction should be kind of easy. So if you've got an original program, and let's imagine it's a high-value application, come back to why that matters in a moment, and we've got some inputs that people care about, and we've got an expected output that we get from those inputs. If we then make a load of these metamorphic injections to get some variance, and we execute them when we find there's a mismatch, okay, so we find that variant I gives a different result from the original program when we execute on the given input. Variant I could be incredibly bloated. I mean, just to put that into perspective, maybe I will just show you one of the shader sets. I'll pick a random variant, variant 4.frag. If I scroll down, you should start to see just like, this stuff here is like injected expression trees. It's absolutely horrendous, right? So really, really huge programs. And indeed, you know, if you just said to a compiler developer, this massive program, trust me, is supposed to do the same thing as your original program, but it doesn't, there's a bug. The compiler developer is not going to take you very seriously. Just to show you, the original program was this. That's it, okay? So we made these really bloated programs. Okay, but all you've got to do is say, right, well, let's undo an injection and ask, do the results still not match? If they don't, good, let's undo another one. Do they match? Okay, they match. Let's put that one back. Let's undo a different one. Do they match? No? Okay, good. Let's undo another one, etc. So you can undo more than one injection at a time. But the fact is, we made the injections. We know what the injections look like. If we can make sure they're always reversible, we can have a greedy algorithm that just tries to reverse injections while we still see a difference in results. And we should end up with a minimal difference to our high-value application that shouldn't make any difference, and a minimal change that shouldn't make any semantic difference, yet does. And that is something we can give to a compiler developer and not only say there's a bug and here's a nice small test case to expose it, but also argue that it's a high-value bug, a bug that really matters because the application is an important application. And we've made a small change that shouldn't change its behavior, and now your compiler miscompiles it. So I think there's a case to say that we can find high-value bugs with this approach. Okay, so what I want to do is first of all mention something, which is that OpenGL essentially has no rules related to floating point computation. The specification, I'll show you what the specification says in a moment, but the specification is rather loose when it comes to floating point results and gives the compiler quite a degree of freedom into the optimizations it might do. So what I'm going to do now is run a script called diff images. I'm going to give that my shader set folder. And what it's doing is it's running over all of the images produced during that run where I asked you to bang the table. It's running all those images, and it's going to report whether the image was pixel level different from the original image, the image produced with no injections. And if it was pixel level difference, what is the histogram distance between the original image and the mutated variance image? Okay? And the histogram distance I'm not going to go into right now, but it's an image comparison metric. So you can see that, for example, the variant 5, its PNG file was pixel identical to the original. You can see that variant 4, its PNG file, had a histogram difference of quite a large number. And if we're lucky, we might see a few cases where we get a very small histogram difference. Here we go. So variant 9 had a very, very small histogram difference. And if I open shader set variant 9, PNG, then this looks correct, right? It looks like a correct image. And this is going to be pixel level different in a whole bunch of pixels, but only by a tiny amount. And because the OpenGL specification is very loose about floating point and lets the compiler have some freedom in what it does, and because we have changed the program, we may change what optimizations the compiler does. So these small pixel differences giving a very tiny difference, they're very likely okay. They're very likely not indicative of compiler bugs. On the other hand, if I open up variant, let's find one that's a bit in between. Let's try variant 13. Okay, this is definitely wrong, right? This looks wrong, and this isn't just going to be the result of a few floating point rounding errors. This looks like something that would be indicative of a compiler bug. So now what we'd like to do is find a minimal test case exposing a compiler bug from this example. So what we can do now is say reduce variant. We give it the vertex shader that we need to give for reasons I won't go into here. And we give it the variant that was bad. So this is going to be shader set variant 13.frag. And we say above threshold to mean I want you to keep making the program simpler while the histogram difference is above some threshold, and there's a default small threshold in the tool. And finally, I'm going to say what the reference image is. So the reference image is going to be shader set recipient.png. So meaning recipient.png, that is the expected image. I want you to keep undoing injections while the produced image is more than this threshold away from the expected image. Make sense? Okay, so if I run this, then what we should see in a moment is the bad image, and then we should see bad image, good image, bad image, bad image, bad image, good image. Basically, every time we see the bad image, we've made a successful reduction. Every time we see the good image, where we saw that we've failed, we've removed something that didn't actually contribute to the bug. So you see the bad image, bad, and after a while, the process, there are a few kind of heuristics to decide when to stop. You stop when you can't find, basically when everything you try and remove causes the good image, you stop. Okay. So we're seeing the good image more and more, which suggests we're getting near the end of the reduction. And you might also notice, I don't know if you can see those square brackets with 0 in them. That really means there's only one more thing we could try and remove. Okay, so we've finished. So we get the reduced shader file is in reduction final.frag. So first of all, let me show you the animation of reduction final.frag. And you can see that it's a very cool wrong animation. Just to remind you, we wanted to see this. Okay, so it's sort of right, but it's not right. And now, one of you asked earlier, I think you asked, how do you know whether the injections are actually inducing compiler bugs? Might they be, just wrong injections? So what I'm going to do is not to, of course, in general, we probably are sometimes, there probably are bugs in our tool, right? But what I can do is I can compare the original file and the reduced file. So at the top here, this is the reduction final. It's got a little bit of, it's got this thing called injection switch, which is a two-dimensional vector that we inject. In OpenCL, we had that dead array I mentioned. In OpenGL, we introduced something called a uniform variable, which is a two-dimensional vector, and we populate it with the values 0 and 1, and we do our trickery based on that value. So that's the equivalent of our dead array. So that's something we've added, but that should have no effect on its own. And then down here, what we've done is, on the right-hand side, we said float divisor is equal to x divided by camera.x. Okay? And on the left, what we've done is float divisor is equal to x divided by a three-dimensional vector of zeros plus camera, which is a three-dimensional vector. So we've added 0, 0, 0 to camera, and then we've looked up the x component of that. So I think that it's pretty obvious that this shouldn't change the semantics of the program. It's of course possible this could affect floating point optimizations. It may be that the presence of this plus 0 might just change what the compiler does. It might be the difference between some optimization kicking in or not kicking in. We can see that it's clearly changing what the compiler does because the compiler is doing something wrong. But the fact is, it shouldn't affect the overall computation of the program unless the program was inherently numerically unstable and prone to being kind of driven crazy by any tiny change in floating point values, which I don't think is the case for this program. So either this would indicate that the program is totally unstable, or it indicates there's a compiler bug. And certainly we can give this to a compiler developer for fixing, and we've given this to Intel, and they say it'll be fixed in their next driver release. Notably, this bug didn't actually require the opaque value injection. I mean, we're not using injection switch. This is something the compiler really should optimize away. Okay. So, yep, I could point you to the bug report online where they confirm this bug. Okay, so going back to the presentation. Right, I argue the approach may be good at finding bugs that matter. Well, I hope I maybe have convinced you about that in the sense that that program that produced the circles, that was something that a GPU enthusiast wrote. It's something that they love, they care about. It really matters to them if that program works. Okay, it's just a program from glslsandbox.com, but let's imagine it wasn't. Let's imagine it was something inside a game engine or something inside the infotainment system in a car. I think if we can make a tiny change to such a program and find that this induces a compiler bug, then that's a sort of scary compiler bug. Okay, you might say, who's going to add a three-dimensional vector of zeros to one of their variables? That's a dumb thing to do. But surely you'd like to think that if you did it, it would work. Whereas with OpenCL, using random program generation, we found quite obscure bugs that involve things like a union inside a struct. And you might argue there that those bugs perhaps don't matter. I mean, I think all bugs matter, but you might argue that that's a bug, that's very unlikely to occur because people don't often put a union inside a struct in OpenCL. But I think basic manipulation of vector data types in GLSL is something that really should work. Okay, so yeah, by starting with a high-value application, doing this process of injecting, testing, and minimizing, we get this minimal difference that exposes a compiler bug. I think we can argue that we can potentially find high-value bugs. And the other thing, which I've sort of alluded to now, is that I think this approach may be well suited to testing compilers for languages with imprecise semantics. So if you were to generate random GLSL shaders and try and compare them across devices, across different GPUs, this probably wouldn't work very well because the language has got these loose rules about floating point. But because we're comparing variants of the same program on a single GPU, we've got much less risk of being prone to terrible differences arising from floating point computation. And this simple image histogram metric sufficed, with a small threshold, sufficed for weeding out the difference between small changes because of floating point optimizations compared with drastic changes because of a compiler bug. So to tell you what the GLSL spec says about floating point, and by the way, this is an issue in other languages with floating point too, not all languages, but many. So first of all, if you've got a denormalized value, that's a value very close to zero, it can be flush to zero, but it can be flush to zero, not must be. So this is something where you might see differences between GPUs. The rounding mode cannot be set and is undefined. So you get these different floating point rounding modes, and what this is saying is that the rounding mode will be one of the IEEE rounding modes, but you can neither set which mode it is nor query which mode it is. It's just going to be one of them. So again, this is going to mean that you're going to get differences between different GPUs. I don't think you'd get the rounding mode changing for a single GPU during program execution, although the spec doesn't forbid that, but I don't see any reason why you would get that weird behavior. Nans, Notta numbers, are not required to be generated, but again, not required. They can be generated or might not be generated. Right? So this means that really testing across different GPUs is going to be hard. And then even tougher, so without any precision qualifiers, which is a detail of GLSL I won't go into, implementations are permitted to perform such optimizations that effectively modify the order or number of operations used to evaluate an expression, even if those optimizations may produce slightly different results relative to unoptimized code. So as a graphics programmer, this might sound reasonable. As someone who's interested in static analysis or formal verification, this is very worrying because what does slightly different mean? Does it have any meaning? What does slightly different inside a loop that's going to execute 1,000,000 times mean? Slightly different can become very different if the loop executes many times. Okay, so this is sort of, you might wonder why is the language so loose? Well, the reason is that OpenGL tried to unify graphics programming for a whole range of GPUs that already existed. It didn't want to bias towards, say, NVIDIA or AMD, ATI at the time. The idea is it should be something that can work across multiple GPUs and can let different GPU vendors play to the strengths of their designs. But from a compiler testing point of view, this is quite difficult. But I would argue that our approach goes some way towards overcoming that issue by making localized changes to programs that can be tested with respect to just one GPU compiler. Okay, so I think I'm done with the OpenGL testing demo. So to summarize this lecture, so compilers, like any other software, can be buggy. Finding compiler bugs that bite you in practice is not that common. Has anyone here been bitten by a compiler bug during their research or software engineering? Actually had a problem that you've eventually traced down to a compiler bug? So I love testing compilers. I can't honestly say that I've actually been bitten by a compiler bug myself, right? Yeah. So they're rare, but they do exist. So random differential testing is cross-checking multiple implementations. It doesn't have to be applied to testing compilers. Anything where you've got multiple artifacts that should give the same results under some appropriate conditions, you can apply random differential testing. It requires well-defined programs. And as an aside, undefined behavior is quite a subtle topic in compilers and has ramifications to program analysis as well. Then I showed you equivalence modular inputs testing from PLDI 14. And then we've proposed this, well, I guess a generalization. We've proposed this injection of dead code and mutation of programs, which is an example of metamorphic testing. It was very much inspired by this EMI testing work. And applied this to GLSL compilers. And as I mentioned, this offers a number of advantages compared with, say, random differential testing. We can find arguably bugs that matter rather than maybe obscure bugs found by a fuzzer. And we can cope to some extent with floating point semantics. And test case reduction becomes really trivial. Test case reduction for randomly generated programs is really hard. If you make a random C program constructed to be free from undefined behavior and find that it induces a difference between two compilers, how do you go about reducing the program to a small program that still produces a difference, but has well-defined semantics? This is something which John Regere's group have got an amazing tool called C-Reduce, which has a PLDI paper associated with it that tries to tackle. It's a really hard problem. We don't have that problem in this approach because we made the injections ourselves, so we know how to undo them. Okay, there are a whole lot of open problems. So I've made these claims about metamorphic testing having some advantages over random program generation or fuzzing, but we haven't actually validated those claims yet, and I think that's an interesting problem. I've claimed that we may be finding bugs that matter. I can just say that Intel have taken the bugs we reported seriously. We haven't yet got to doing larger scale testing. But I think this issue of finding bugs that matter is a very interesting issue. There are people, as I'll show in the next slide, can be quite skeptical about things like compiler testing methods because they may just find bugs that no one cares about. Like Jeff said this morning, all software is buggy. So if all software is buggy and is always going to be buggy, what's the point of just finding bugs? You want to be finding bugs that matter. You don't want to just be finding bugs because presumably you have an infinite search to find bugs if there are always bugs. Right? Finding bugs that matter is important. A problem with fuzzing and with mutations is this duplicate bug problem. So if you randomly generate programs to find compiler bugs, if there's an easy to induce bug, you just keep triggering it. And it can be hard to find any other bugs until you fix that bug. With our program generation, that bug I showed you where you add 0 and you make the compiler misbehave, that's kind of the only bug we can find in that driver right now because it's so easy to trigger. It's almost certain we're going to trigger it. It would be interesting to know how you can avoid that problem without waiting for the next release of the driver or compiler. Like, is there a way of learning what the nature of that bug is and avoiding generating programs that are going to trigger it? I wonder whether the images we get from the programs might indicate what bugs they're triggered by. And one thing I'm interested in is testing program analysis tools. Do you trust your program analyzer? That's something that my colleague Christian Kadar and I are kind of interested in these days, and we're interested in applying some of these techniques to testing program analysis tools. Just as a bit of fun, not everyone is so keen on compiler fuzzing, so I was made aware via Twitter of this guy, Derek Jones, who's got a blog post at this URL. So he says that when compiler fuzzers started to attract a lot of attention a few years ago, the teams working on the main two open source compilers, GCC and LLVM, were quick to react and fix many of the reported bugs. CSmith, the tool I mentioned earlier, is the fuzzer that led the way. So it's definitely true to say that CSmith led to the identification and fixing of hundreds of bugs in GCC and LLVM. Okay, so he's not exactly saying whether this was good or bad, but I read this as a positive, that there was a good reaction. Okay, it says these days finding bugs in compilers using fuzzing is old news, and I suspect that the teams working on GCC and LLVM don't need to bother too much about new academic papers claiming that the new XYZ technique or tool finds lots of compiler bugs. And he goes on to make a stronger statement, which is, in fact, I would suggest that compiler developers stop responding to researchers working towards publishing papers on these techniques and tools. Responses from compiler maintainers is becoming, his words, not mine, becoming a metric for measuring the performance of techniques and tools. So responding just encourages the trolls. And the emphasis is mine, not his there. So, I mean, I can sort of see where he's coming from in the sense that certainly if you want to get a paper at a top conference, you have to say that you found bugs. Maybe that's silly, I don't know. I mean, the fact is we're just testing human-made artifacts that have a certain level of quality right now. So the fact that we found bugs in them today versus maybe trying to write our paper a year later when they might have coincidentally become more reliable. I mean, sometimes it does seem a bit weird that people place so much emphasis on, did you find real bugs? And I definitely think it's true that as an academic, if you want to get your work published, you have to find some bugs, and it's really useful when people respond. I don't regard personally this as being intentionally unhelpful work. I mean, I think it's fascinating to see whether one can find defects in complicated and subtle systems and find a range of defects. There are lots of interesting research questions to answer. Anyway, but I thought this was an interesting attitude, and it made me wonder, you know, when we report these compiler bugs, do people think, oh no, not another bug, or do they feel embarrassed about the bugs or shamed into fixing them rather than thinking they should fix them? I think that's quite an interesting social problem. So there you go. Okay, so I would recommend, if you're interested in compiler testing, reading the paper about the C-Smith tool from PLDI 2011 and the paper I mentioned from PLDI 2014 about compiler validation using equivalence modular inputs. I think these are fantastic papers, not just if you're interested in compiler testing, but if you're interested in how to write a really good paper. I would recommend reading them. And also the paper about test case reduction for C compiler bugs is a good read too, and raises some interesting issues related to undefined behavior, for example. And then we've only got into this work quite recently, so we have this study from PLDI last year about OpenCL compilers, where we explain this dead code injection technique. And we have a very short paper about the work on GLSL I presented today that appeared at the Metamorphic testing workshop a few weeks ago, about which we want to publish something more substantial in the future. So on that note, thank you very much for your attention for both of the tutorials. It's been a pleasure to be here. Unfortunately, I'm leaving tomorrow morning, but I'll be around now and can be around this evening if you want to talk more. Okay, thank you.